my name is Victor. I'm a PhD student in computer vision and specifically medical image analysis at electrical engineering. And today I'm going to talk to you about using images, specifically medical images, to generate predictions from AI. For example, a diagnosis from an X-ray, a prognosis from a PET scan, and so on. And the big conundrum that is actually explaining what the AI did and how it used the images to generate its predictions. So I'm not alone, of course. I have my supervisors, Ida and Jennifer from Chalmers, and also collaborators from Sahlgrenska University Hospital, Matthias and Lisa, for example. And I mostly work with something called vertebral fracture risk prediction. But today I'm going to talk about medical imaging in general. So this is how it typically may look. This is a chest X-ray of a young girl who presented at some point with pneumonia-like symptoms. Anyone who's sort of been in the healthcare chain of care knows that typically you present with some symptoms, you go to the doctor says, well, we might need to do an X-ray, and then a radiologist is tasked with actually looking at the X-rays and give some sort of note or judgment. So this is a case that happened with this girl as well. And what the doctor said was a young girl presents with bilateral lower lung zone predominant consolidations and ground glass opacities indicative of inflammation in the alveoli. This is, of course, medical speak. The point of it was that it was basically a diagnosis for COVID-19, which was the radiologist's judgment. And this, of course, is extremely important, and normally what you would get in your patient records, for example, some sort of description and observation from your medical images, and hopefully a diagnosis based on this. However, the problem with these is that the acquisition and examination of these images is typically quite arduous. It takes a lot of time. For example, during the COVID-19 pandemic, the influx of these chest X-rays was just tremendous in hospitals. And in order to sort of accelerate the workflow and let people, the radiologists, get some breathing space, AI models, for example, were employed in order to be used as decision support for the doctors. And this is not completely without precedent. Using AI as a diagnostic tool or prognostic tool that is saying something about the future is well established already. For example, in breast cancer detection, skin cancer classification, these are typical melanomas, and also, for example, in diabetic retinopathy, which is basically an eye disease which may be spotted. Oh, really? There's maybe one who's got that now. And these may all be diagnosed very, very well at this stage with AI tools, actually, at least on par with human doctors. And that's, of course, great. What I will talk about today is a slight issue with using these models and the research that we're basically trying to address in our group. Because if you supply an image, for example, the chest X-ray I showed previously, to an AI, it won't really say anything. It's a tool, it's like a program on your computer, basically. It won't say anything, but it will be giving you a diagnosis. COVID-19, for example, will give some sort of confidence, a percentage of how certain it is of this diagnosis. The problem is that this is inherently quite unhelpful, because this doesn't really make us understand anything else than that this was a diagnosis. When the patient hears this, they might know, well, why did you think that I have COVID-19 specifically? Well, you tested for this antibody, for example, is something very specific a doctor would say. Other doctors might want to be able to validate a result, learn something from it, and so on. That is impossible when we get justifications or reasoning like this, or non-existent ones. In reality, rather, what happens for a doctor is that you give them some sort of input, an image, for example, and if we see the doctor as a program, they will generate a reasoning of some kind. This is the same we saw previously. But what the doctor actually does in practice is that it synthesizes this reasoning into features in practice. The patient is young, has consolidations, a high opacity on both sides of the lungs, for example. And if we want, we are able to go from the diagnosis that is based on these features and actually get basically an explanation, where does that come from? And this is often grounded in clinical protocols, for example. If all of these are fulfilled, then we get the diagnosis COVID-19, which is a lot more transparent. It yields a more reliable and trustworthy point of care, and it also saves a lot of worry for patients, for example. An AI, which many have seen before, and maybe someone else will talk about this today, it's typically called a black box. We know how it works, like mechanically in there, but we don't really know exactly how the answers are practically being generated from the input, the image, for example. We don't know how the information in the image is being used and mechanically how we get the diagnosis of COVID-19. And not getting any motivation at all is not useful. And in practice, if we want to proliferate the use of AI, specifically in medical image analysis, this will not be accepted, not by doctors, nor by patients in practice. So what we are trying to research is trying to explain what AI actually sees. And we're going to approach this from 3 different steps or directions. First off, we're going to see if we can tell what does the AI see, and if that is enough, how it's being used, and maybe if we can even put it into words. So for step 1, we'll try to highlight the parts of an image that are being used by the AI. And for this, there are actually quite established methods. One of them is called GradCam. This is quite technical, but nonetheless, it works by basically inspecting what pixels in an image would change the prediction if I altered them. So for example, in the top row, we're trying to classify if there's a dog in that picture. If I change the pixels where there is a dog, that would clearly probably change the outcome. If I completely remove them, maybe the AI would say there's no dog. So those pixels change the outcome. If I change the cat, that won't change the outcome because there's still a dog in the picture. That's the intended use, at least. And the same thing for the cat. So this is a very well-established method, and it's used all over computer vision research. It has some nice highlights. For example, this is an example of a chest X-ray model which is supposed to predict if a patient has pneumonia. It turns out that it didn't predict whether a patient had pneumonia or not. It looked whether there was an L up there, which is a small sort of metallic thing they put on the patient, and it seemed that that correlated much better with whether they had pneumonia or not. So it didn't actually see anything of relevance to the actual outcome, only associations. So that's a true success story of this types of method. There are similar ones that do similar things. Here is something called attention, that basically say what parts of an image are useful for the prediction. Could we leave some out, for example? And here we have 3 different diagnoses by an AI, a healthy patient, one with pneumonia and COVID-19. And we can see that, sure, in the healthy case, it seems to kind of look at the spine and the shoulder, so that's not very informative, I guess. But on the pneumonia and COVID-19 cases, you can see that it does look at the actual lungs. It uses that information. We know a priori that the inflammation of the lungs is very important and indicative of whether you have these kinds of diseases already. So it kind of conforms to our biases of how it should work. And that's reassuring, we think, at least now. The problem is that these methods, they have a tendency to not necessarily agree with each other. So these are 3 different neural networks, AIs, that have been given the same image of a retina and made the same predictions, but completely different estimates of what they actually see. So the top row, there's no coherence at all. The middle row, they basically agree, and the bottom row, not at all. So one might be inclined to say, well, surely medical doctors disagree as well. And yes, of course they do. However, they do still have clinical protocols of what they should look at in order to sort of make a diagnosis. The AIs typically do not have this kind of biases built in already, which makes it kind of concerning that they can use so different kinds of information and still come to the same conclusion. Either we have completely misunderstood how something works, or maybe this method doesn't work as we thought in terms of highlighting. Another example is in terms of, in the case of PET. So this here is a heat map from a PET scan. It's not the same heat map I showed before. This rather shows the uptake of a radioactive sugar tracer that you swallow, and it then gets metabolized in your body, especially, for example, in the brain, where a lot of sugar is being used, and in the bladder at the bottom, where a lot of it is excreted. But also by tumors, for example, in lymphoma, which is the case here. They love a bit of sugar, it turns out. So in this case, we're going to look at the application of predicting whether a patient with lymphoma, the prognosis or risk of dying from this. So we give it to an AI, and the AI makes this prediction, high risk of dying from lymphoma, and it attributes it to these areas. And that kind of conforms quite well to what we thought originally, right? So these black dots in this case are the tumors. So we would want it to focus on the tumors, right? Because those are very indicative of whether they die or not. However, if this had instead generated a heat map focusing, say, on the liver or on the kidney or something like that, would you then call that a good explanation? It's hard to say, right? Well, is it a good explanation? We don't know. We don't know how it's been used to begin with. We assume that this is a good explanation because it conforms to our prejudice that these areas should be useful. So a slight issue with these kind of models is that we have a tendency to only accept the explanation, the visual explanation that we get, if it actually conforms to our biases. So it should highlight a dog if it classifies a dog, for example. But I don't know, maybe sort of it's in a kennel. The picture is taken in a kennel or something like that. Then the kennel itself is indicative of whether there's a dog in the picture or not. It shouldn't just focus on the dog. And this is a huge problem with these kinds of explanations. And typically it means that it is not sufficient to look at these visual explanations. Here's another example of melanoma, or a potential skin cancer, at least on a pale person like me. This is a spot, and we want to see what the risk is from that there is actually malignant melanoma here. The AI says medium. Okay. Sure, that's not very rewarding. So we use these visual explanations to see if we can get some more information how this prognosis comes by. Ah, yes. Now it's all obvious. It's used to spot. Thank you. That's great. That's all we learned from this now. It's that it's used this spot. Well, I assumed it used the spot already. But I figured maybe like the shape, the texture, the color would have been useful. Things like the doctor would have said. It's speckled, it's round, it's uniform in color. There's a low risk. That's what the doctor would have said, not the AI. So in reality, we get from these explanations very little. I would even go as far as to say that highlighting pixels doesn't really explain anything. It's nice to see that it sees something and uses something in the image, but we don't really get it explained. So we move on. How are things being used? What we can do instead is that we extract explainable features, for example, that we know are useful already using AI, and then we apply, for example, classification or risk prognosis. We can, for example, in the case of lung nodules in CT, find that they may be round and solid and large, they may be speckled, hollow, and so on. And We can extract these features using, for example, AI, and then we can use those in a later downstream task of classifying the risk, maybe according to the clinical guidelines already used by doctors. Another example is, for example, whether a vertebra is injured or fractured or not, like in the case of a spine X-ray there on the right. We can first extract visible points, and then we can actually calculate predictably whether there's a fracture or not. Another alternative to this is to use what's called similar known examples or prototypes. So prototypes, this is basically how many doctors and people work. We have kind of a database, and doctors especially, a database of, say, a patient who's healthy. What do they look like? A patient with pneumonia, what do they look like? And what we do is that we build a database of, say, healthy people, a healthy X-ray, and we can make a classification whether they are diseased or healthy by looking if they are most similar to the archetype or prototype in this category. For example, this gets the shape of the heart from a known patient who is healthy, a lung opacity in the upper lungs that comes also from a patient who is healthy, and so on. And aggregated, this should mean that the patient is healthy. And that also reasons very well with how humans sort of make their decisions already. We base it on previous experience, and here we can actually point that out. As this is just a graphical illustration, maybe there could be a drawn number, and which one is it most similar to? And we have kind of prototypes of different kinds of 2s and 3s in this case. And we can choose basically which one is the most similar, but numerically, of course. So, thirdly, if we have explainable features of some kind, we need still, ideally, to put things into words. And in recent times, vision language models, like ChatGPT nowadays is a vision language model, Gemini and so on, are helpful in generating text that may help us to actually explain things in a way that doctors and people are comfortable with. This is an example of a model made by NVIDIA, which takes, again, a chest X-ray. There's lots of data on chest X-rays. That's why these are the main examples. It makes a judgment just based on the image. I'm not going to say exactly what it says, but it's capable of making some sort of medical-sounding judgment of how the image looks and motivating it in a manner that would be similar to a human doctor. Indeed, a generative AI would function almost identically to a human in this case. Given an image, it could generate AI descriptions. It could sound exactly the same as the one we got from the doctor previously, and even get a diagnosis, for example, COVID-19. And this, of course, is a kind of holy grail, and especially if you can combine this with the explainability of certain known features that we know are important, and also finding what exactly in the image that it looked at when using this kind of reasoning. If we're there right now, though, I wager we are not. This is not a medical AI, but I did try this on Microsoft Copilot that is not medically trained at all. Don't try this at home, so to speak. But the discrepancy is quite funny, because we know from the doctor that said it's bilateral consolidations, opacities, and inflammations in the image. Copilot says, no obvious large opacities or consolidations. Lungs are visible and relatively clear, and there are no obvious abnormalities. Oh, well done. Nice. The problem is that if we got that kind of description, it sounds very, very medical, and we're inclined to believe it as is. And if we get something, an explanation that is very nice and explained, but completely wrong, again, we are inclined to sort of take things that conform to our biases already. It sounds medical. So ideally, we would do something like this. We would combine actual vision, seeing what in an image is important, how that is being used, for example, but then hopefully being able to inform, say, a vision language model or something that puts this into human explainable terms, like a human doctor. We're not there yet, but this is what we're working with at least. I'm very happy that you've been listening to me and what I've been saying today, and maybe you have the opportunity, if you're interested, to actually work with this, because my group and my supervisor is looking for a PhD student working on specifically vision language models, actually, for medical image analysis. So if it sounds interesting, you definitely have an opportunity to apply now. Thank you very much.
Thank you so much.